Alright folks, hope everybody is doing well and enjoying their Tuesday evening. Just wanted to record a stats video. This is problem number 6. Let's take a look here. It says a study was designed to explore subjects' ability to judge the distance between two objects placed in a dimly lit room. The researchers suspected that the subjects would generally overestimate the distance between objects, and that this overestimate would increase the farther the objects were. The two objects were placed at random locations before a subject estimated the distance. After each subject estimated the distance, the locations were randomized before the next subject viewed it. They collected data for 40 subjects. Two linear models were fit to describe the relationship between perceived distance and actual distance. Provide interpretation for the slope in Model 1. So Model 1 says, for every 1 centimeter increase in the x value, which is actual distance, in actual distance, the perceived distance increased by 1.08 centimeters. 1.08 is the number, that's the slope. Centimeters is because the tells the data is in feet. Feet. Let me change this. Feet. That's A. B. Explain why the researcher might perform Model 2 to Model 1. So when I look at this, it's actually a little bit hard to tell, right? So like Model 2 seems worse, right? Standard error is higher, but here's the big but. Model 2 might be better in this context. Why might Model 2 be better in this context? Well, see, Model 2, what's the big difference? Model 2 has an intercept, right, of 0. Right, there's no intercept here, so the intercept must be 0. Meaning that if x equals 0, y equals 0. So in other words, if the actual distance between two objects is 0, I mean, if two objects are touching, here's one object, here's another, they're touching, and the actual distance is 0, what are you going to say? Well, they're touching. If I'm guessing how far apart these are, and they're touching, I'm going to say, oh, they're 0 feet apart. That just makes logical sense, right? So the model, when I plug in 0 for actual distance, in other words, when the objects are touching, like they are now, the perceived distance, y, what people guess, should also be 0. It's obvious when two things are touching that the distance between them is 0. So I want a model that when I plug in 0 for distance, I get 0 for y. That does not happen over here. Over here, when I plug in 0, I get 0.238. That doesn't make sense. But here, when I plug in 0, I get 0. That's why Model 2 is better. So, because we would expect, right? We would expect what? We would expect that if, let me move this up, actual distance is 0, y should be 0, which B happens in Model 2. Alright, C. Using Model 2, test the researcher's hypothesis that in dim light, participants overestimate the distance, with the overestimate increasing as the actual distance increases. So, if the overestimate increases as distance increases, that means as x goes from 2 to 3, y must increase by more than 1, right? If x goes up by 1 and y goes up by 1, then that doesn't say that we are increasing, right? In other words, if this number is higher, then y should be higher, right? In other words, they're saying if the actual distance is bigger, then y should get bigger, which means this slope has to be bigger than 1. Why does the slope have to be bigger than 1? Because if this was 1, right, if this was y equals 1 times x, what would happen? If x was 3, y is 3. If x is 4, y is 4. If x is 5, y is 5. Then the overestimate is not increasing as this one goes up. Then as this one goes up, this is still staying with an increase of 1 unit. If this is bigger than 1, then if I plug in 3 and then 4, the y increases by more than 1 unit for every 1 unit increase of this. Basically, I'm saying this slope better be bigger than 1. If the slope is bigger than 1, then as the distance increases, this increases by more than just 1. And they want me to do a test on this. So this is a, right, t-test for slope. Again, it's t-test for slope because I want to look at the slope, which is what happens when as actual goes up, y changes based on the slope. The slope needs to be bigger than 1, so I'm going to say beta is equal to the true slope between perceived and actual distance. The null, beta equals 1. The alternative, you don't really need a hat here, is that beta is greater than 1. The conditions, it says assume, right, they're met. Math t-stat equals to beta minus 1 over standard error, which is what? Well, 1.102 minus 1 over 0.393, which equals, going to go to my calculator now. So t-stat, let me get my calculator. Going to go to stat, test, linear regression t-test, statistics, test, sorry about that. Hold on 1 second. Excuse me. Coming back, right? So I'm going to stats and tests, right? And I go to linreg t-test and I'm like, oh my god, this is making me plug in data. I don't have data. So what do I do? Well, this is where you need to step back and say, well, I can solve this. Let me solve this right now. So what am I going to get? I'm going to get, well, 1.102 minus 1 divided by 0.393. This is 0.259. That's my t-stat. Now our question is, how do I get the p-value? Alright, so when I look at this, I'm like, how am I going to get the p-value? That's actually very difficult, right? But we can step back and attack this in a way that is very similar to how we have attacked chi-squared in the past, right? No need to worry about getting the p-value. You don't really need it because here's what you can do. This is why drawing the picture is so important. Here's 0.259. We need to find how much is this, right? Because we're saying greater. Now, if we go to our table, t-table, and now the question is, let's write here our degrees of freedom. Degrees of freedom are, let's look at the problem here. How many did they sample? They sampled 40, so the degrees of freedom are 40 minus 1, so 39. So if I go to my table, with DF of, let's say I use 30, and I go to 0.05, the number I get is right here, 1.697. So 0.05 is right here, 1.697. This is 0.05. So the green has to be bigger than 0.05. This is how we did the chi-squared, right? Looking at the critical value and then drawing the picture. So I'm just going to say because the p-value is greater than 0.05, we fail to reject the null and conclude. And remember, when you're writing the conclusion, look back at the original question. What do we conclude? We conclude that the overestimate does not increase as the actual distance increases. And we cannot conclude the estimate increases as distance increases. So I hope everybody understood this. This is very crucial, right? We took 0.59, we said 1.697 is 0.05. So this has to be bigger than 0.05, so therefore we're going to reject it. Let's see what comes next. Now we have the researchers also wanted to explore whether the performance has differed between subjects who wear contact lenses and subjects who do not wear contact lenses. A new variable was created to indicate whether or not a subject wears contact lenses. The data for this variable were coded numerically. 1, so if this is 1, I wear contact. If it is 0, I do not wear contact. And contact, so here's the new model now. So if this is 0, this goes away. If this is 1, then it's just 0.12 times the distance. Alright. And what is asking us here? Using Model 3, sketch the regression for contacts and non-contacts. So let's do with contacts. So actual distance. If the actual distance is 0 with contacts, what happens? This is 0, so these all go away. So it's going to be 0, 0, right? This is 0, 0, everything goes away. So this starts off at 0, 0. Now what if this is 1? If contact is on and actual distance is 1, what do I have? I have y hat equals 1.05 times 1 plus 0.12 times 1 for contact times 1 for actual distance. And what do we get? We get 1.17. So 1.17 right there. What if this is 2 for contacts? 1.05 times 2 plus 0.12 times 2 times 1. 1 for contact, 2 for distance. And this is 2.34. So 2.34. What about 3? So I plug in 3 here now. 1.05 times 3 plus 0.12 times 3 gives me 3.51. 3.5, and we get something like this. And I'm going to write this is contact. Alright, so now what happens if I don't have my contacts on? So that means if contact is 0. So this goes away now, right? If I don't have the contact, this is 0. 0 times anything is 0, so this goes away. It's just 1.5 times x. So if I plug in 0, it goes through 0, 0. And the slope is a bit flatter. So this would be non-contact. Right, so that's all they wanted there. And finally, part E. In the context of this study, provide an interpretation of the coefficients for Model 3. So let me rewrite Model 3 here. Model 3 says 1.05 times actual distance plus 0.12 times contact times distance. 1.05 times actual